old exam, you know, I didn't present the material in the same way. And this is from 2017. And so at this time, I didn't cover as many of the chemical reactions. I decided to push that to later. But this time, I covered all of them early. And so one thing that exam 1 and exam 2, these old exams, is missing are more chemical reaction problems. And so I gave you the worksheet. The worksheet would be kind of like the type of problems you could expect on the exam 2, which would be, you know, like a metathesis, maybe a bronzite acid base.
Who are you going to give us the Lewis?
Lewis is possible, but Lewis is, you know, it would be like the quiz, let's say, you know, something. Lewis is more complex.
Well, actually, I do have a question. For our exam coming up next week, will we have a similar question to what we had yesterday? The change in temperature?
No, you won't have a question like that. In fact, so what you could do is you could eliminate the chapter 7 problems from this test. There are some chapter 7 problems in this old exam. For example, 29, read chapter 7, 30, 32, actually 31, 32. You know, anything that deals with energy won't be on your test. Instead, you'll have some more reaction type problems to do, like the worksheet style problems, skeleton, bronzite, metathesis. Is that clear?
So no chapter 7?
No chapter 7 on this.
So 4, 5, and 6?
4, 5, and 6, and then 5, you're going to have more chemical reactions. But in the homework for 5, there aren't enough like practice problems, so that's why I gave you the extra sheet. The extra sheet is you don't have to turn that in. All right, so you want to work through this and work through the worksheet too for preparation for the test. Okay.
Can you?
There's what question on the homework was that really? Question on homework?
Oh, yeah. Number 25 on the chapter 6 homework.
Number 25, chapter 6. Let's take a look at that. Okay.
I could do it Tuesday in the morning. I have something coming up.
25, a constant volume vessel contains 12.5 grams of a gas at 21 degrees C. If the pressure of the gas is to remain constant as the temperature is raised to 210 degrees C, how many grams of gas must be released? So, this particular problem, you know, when we have a gas with certain conditions and when we change the conditions, then we're going to use the combined gas law. T1 V1 over N1 T1 is equal to P2 V2 over N2 T2. All right. They say constant volume, so the volume doesn't change. And they also say it's going to be pressure they want to maintain the same pressure, so pressure doesn't change here. And so we end up with this scenario here. And so what we're going to do is we're going to just take this one and then just come up with some kind of ratio. And so what has to happen is the amount has to change. The amount of gas has to change. And so we start off with a certain number of moles of gas and we end up with a certain number of moles of gas. And so we're going to solve this equation for N2. And so, you know, what I'm going to do is I'm going to multiply both sides by N2 and N1 and T1. And so we end up with T1 over T2 and N2, N1, sorry, like that. And this will be the temperature factor here. And the temperature goes from 21 degrees C, which is T1. We have to use Kelvin. And so this would be 294 Kelvin. And then T2 is going to be 273 plus 210, which would be 483 Kelvin. And now the problem is we don't know what N1, this is the question, what do you put in for N?
No, I was just like really confused because I was able to solve it, but then I didn't understand like what the numbers were because I knew that the moles should increase. It seemed like they were decreasing. I don't know. I'm just confused as to like what we're actually solving.
We're actually solving for how much gas we have to lose in order to maintain the same pressure. If we have the same amount of gas, then the pressure is going to increase. And so what we're looking for is a change in the number of moles. So whatever we do, we have to remove some of the gas out of there, otherwise it's going to build too high. The pressure is going to be built too high. So this is like if you have a pressure relief valve. If you have a pressure relief valve, what it's going to do is it's going to allow the gas to escape. And so this calculation is how much gas will escape out of the pressure relief valve. And so in order to maintain constant pressure. So we want to know how many moles of gas will escape. But the situation is they don't give us moles. Instead, they give us grams. But they don't tell us what the gas is, so we can't calculate the molar. We don't know what the molar mass is, and so, but did the gas change? I mean, did they put in a different gas, or is the gas the same? The gas is the same, so the molar mass doesn't change necessarily. And so, what N1 is equal to, and N2, N1. Let's just write it up here. N1 is equal to the mass of the gas times the molar mass of the gas. And so I'll use this symbol for the molar mass of the gas. And so this is the mass 1 of the gas. And N2 is equal to the mass 2 of the gas times the molar mass of the gas. And so here for N2, we'll just plug that in. It's going to be the mass 2 times the molar mass of the gas. And this is going to equal this is going to equal 294 over 483. It's less than half times N1, which would be the mass 1, times the molar mass. Since the gas didn't change, the molar mass stays the same, so we can cancel that out. And so we'll just see what it comes out to. So you got the correct answer? Okay.
I didn't, but then I looked at the solutions guide and the way they explained it like made no sense to me.
12.5 times 294 divided by 483.
So your question.
7.6.
Yeah, well, kind of.
So
It's like the number we solved for the temperature ratio is really kind of.
So what's going to happen is this. You start off at 21 degrees C. This is a gas that's sealed in here. And there's going to be a pressure relief valve here. And this is going to be a pressure, P, let's say P1. What happens if you heat this? Well, the cylinder volume can't change. And so what's going to happen if you heat this? Well, the pressure is going to go up. And so if we heat it, the pressure goes up. But if we have this pressure relief valve, we can make sure the pressure stays the same. And so what that's going to do is it's going to just bleed off gas. And so here we're going to start off with 12.5 grams. And then over here, we're going to end up with 7.6 grams. 7.608 grams. And so that means we have to lose, how many? 4.9 grams. So 4.9 grams of gas has to bleed out of the pressure relief valve. Otherwise, the pressure is going to go higher than P1. Does that make sense? And so that's what we do. So this is a combined gas law with an extra step. The extra step is they give us grams instead of moles. Sometimes, you know, we do it. But does that answer the question for this?
Yeah, I haven't done the calculation wrong or something, because I'm still not getting the right number. Maybe my like Kelvin conversion was wrong. But they had done it differently in the solutions manual.
Actually, I don't know how they did it in the solutions manual.
They left the temperature.
Okay.
Maybe not, but they got a different number.
Okay.
So
Well, we could rearrange this. You know, rearranging this, you could do different things. Like the ratio of T2 to T1 is equal to the ratio of N1 to N2. So what we say is that these are inversely proportional. So if one goes up, the other has to go down, you know, to maintain it. And so if the temperature goes up, then the moles has to go down. That kind of thing. I don't have my solutions guide. Let me take a look. Just do it like this way or something, I would think, yeah. Okay, were there any other questions?
Number 22 and chapter 6.
Number 22. Chapter 6. Scuba divers know that they must not ascend quickly from deep underwater because of a condition known as a bend, discussed in chapter 14. Another concern is that they must constantly during their ascent to prevent damage to the lungs and blood vessels. Describe what would happen to the lungs of a diver who inhaled compressed air at a depth of 30 meters and held their breath while rising to the surface. So if they held their breath, I just yeah, no, it would have to expand or their pressure would have to go up.
yeah.
Unless it's very fluid, they will be crushed.
Yeah, so if they're at a depth of 30 meters, let's say these are the, this is the lung volume here, this is air. Then we have to figure out, this is, you know, we don't have to do a detailed calculation for this. We just do 30 meters depth is about, how many feet? 90 feet, roughly. And so 90 feet of water is going to have how many atmospheres? A lot. Yeah. So if you're down here at 90 feet, about, just roughly, about how many atmospheres of water pressure is there? How many pounds of water? About, yeah.
1 atmosphere of added water, so it'd be 3 additional atmospheres.
Yeah, 3 additional. So you have 1 atmosphere of air, 14.7 pounds here. So about 15 pounds of air, plus about 45 pounds of water.
Is it for 30 meters or 30 feet?
I thought it was for every 30 feet.
It's a
30 feet.
That's 90 feet right there. So wouldn't
Yeah,
it be
so-
more than 3 atmospheres?
Wait, is it 90 meters or 90 feet?
It's 30 feet, roughly 30 feet
it's
per
30 feet.
atmosphere, so that would be third.
I thought 30 meters was roughly like.
Yeah, but
99
this is 90 feet that we're at right now.
Yeah, this is 90 feet. And so we're at 90 feet depth, so that's going to be about 3 atmospheres of water, liquid. And so this is 3 atmospheres of water, 1 atmosphere of air, and combined it's going to make 4 atmospheres. So we're taking air at 4 atmospheres, and then we're going to bring it to 1 atmosphere. So this has got to expand, right? It's got to expand. And if it can't expand, the pressure's got to go up. Because, because this is the 3 atmospheres. Actually, I was going to do my demo yesterday. Did I leave my cans? Have you seen atmospheric pressure demo?
No.
Let me just do that. It'll start to boil out.
It explains why your tongue, the saliva on your tongue boils whenever it's in a vacuum. Like if you're in the vacuum of space.
Oh yeah. That would be pretty horrible. Okay, other questions? All right.
So when we go up, we add 1 atmosphere because we add 1 to start, and why is that?
When you're down here, in order to fill your lungs, there's 4 atmospheres of pressure trying to compress your lungs closed, or an additional 3 atmospheres or lungs. So you have to really force the air into your lungs, I think, and then I suspect, and then when we go up, that pressure decreases. We're not adding; we're decreasing the pressure as we go up. So it's a little bit different from that demo. But it's just to show you that's a lot of weight on your lungs. It's like when you get into those crowded situations, like in South Korea, remember the stampede that they had? And their lungs were getting collapsed from being compressed with so many other people, and they couldn't inhale. I mean, if they could inhale, there's too much pressure on their lungs; they couldn't inhale. And so they ended up suffocating, which would be pretty miserable, I think, way to die. And I don't know if there's any. When I first learned how to rock climb, we had these things called Swami belts that you wrap around your waist. And the problem is if you fall with a Swami belt and you go unconscious, then they say you have about 4 or 5 minutes to live or something, because the Swami belt will just start compressing your lungs as it creeps up. And then if you're conscious, then what you're supposed to do is you flip upside down. And you learn these techniques for surviving a Swami belt fall. But that kind of stuff. What's that? The purpose of the belt? Nowadays they have harnesses, but back in those days they didn't have harnesses where you could kind of sit down with legs in relative comfort. The other thing is a lot of people like those Swami belts because they gave a lot of freedom of movement. You didn't have a harness binding you; you just had this belt. And usually people use 2-inch webbing around, like a bunch of wraps. When I first started, it was 1-inch webbing. You wrap it 5 times and then you tie a knot. Yeah, and it's very painful if you fall. Yeah, it isn't supposed to be fun. It's supposed to be a little bit of pain and misery, so you can feel alive with things. Yeah, it's a lot different now. All right, other questions? Okay, we're going to go back to this chapter on gases, and I'm going to finish things up with the gases. So we talked about the applications of the ideal gas law. There's some problems. In there. take a look at the next topic. Yeah. Gases and chemical reactions. We have gas stoichiometry. So at the heart of stoichiometry is the mole conversion. So we go from moles of whatever, A, that we're looking at, and we convert that to moles of B. We do this using the balanced chemical equation. So if we have the mole ratio, we can go moles of A to moles of B. So we have to keep track. You know, some people don't even label, like, for example, like the KClO3 lab. Some people don't label what moles they're talking about, and so sometimes they get it mixed up, you know, moles of KCl3, moles of O2. And since they didn't label, they just have moles. Sometimes people use moles of KClO3 for moles of O2. Doesn't work though. So, but we can go straight to moles in two ways. One, we have the volume, and we have the temperature, and we have the pressure of a gas. Then we can go to moles of gas. And so this would be gas here. And the two ways that we can do it is, number one, we can just use the ideal gas law. The moles of gas is equal to PV over RT. Or two, we could use the molar volume. We'd have to flip it over, use molar volume as a conversion factor. And so one of the molar volumes I like to memorize is under normal conditions. Normal, ambient. What are normal conditions if I'm at sea level? Room temperature, 25 degrees C and 1 atmosphere. And so if I already have that memorized, do you recall what that number is? Well, it depends on how many sig figs you want. You know, if we do this to 3 sig figs, then it's, what was it?
3.18 joules per gram per
That was a different one, but it's 24.5 liters per mole. Or if you wanted to 4 sig figs, then what was it? It was 24.46 liters per mole. Was it 4.6? Yeah. And so it depends on how many liters. If we had 24.46 liters, then we'd have 1.000 moles of gas. We can figure it out. And it depends on if B is a gas. If B is a gas, then we can calculate the volume of the gas. And so if B is a gas, then we could get to the volume of the gas. We can get the volume if we know the temperature and the pressure. Because we could do the same thing. We could use ideal gas law. Volume is equal to nRT over P, or we could use the molar volume as a conversion factor. But if A and B are gas, there's a simpler way of doing it. And the simpler way of doing it is this. We could use Avogadro's law. With Avogadro's law just says that the volume is directly proportional to the number of moles. And so instead of having a mole ratio here, we have a volume ratio for this. And the volume ratio is going to be exactly the same as the mole ratio. As long as the pressure and the temperature are the same, volume ratio at constant temperature and pressure. And so when we look at the moles, let's say the moles of A is equal to the pressure of A times the volume of A divided by RT of A. And the moles of B is going to equal the pressure of B, volume of B over RT. of B. Now, if the pressure is the same, A and B have the same pressure, then that's a constant. And if R, actually R doesn't change, and the temperature is the same, then what we see is that N sub A is just going to equal a constant times VA. And this is equal to constant times VB. And the two constants are going to be the same if P and T are constant. That is, if P and T don't change. And so we can just use the volume ratio instead of the mole ratio here. And so that makes gas stoichiometry easier. And so there's some problems with gas stoichiometry. We can take a look at it later. 6.6, I want to look at mixtures. So this is just the overview here of this. Avogadro's law is the way to go. But the problem is people are a little overzealous in this. And so both species have to be gas. If one's a liquid, Avogadro's law doesn't work. Avogadro's just works for gases. Or if one's a solid, it doesn't work. So you have to keep that in mind. It's easy, but it can be misused. Well, I talked about gas mixtures earlier for experiment, the KClO3 experiment. And let's take a look at air here. And we're going to just take, should we take 1 mole of air?
Yeah, 1 mole of air.
All right. So I'm going to take 24.5 liters. Is that 1 mole? Air is a mixture. Is it possible to have a mole of air? It is. It's possible, but a mole of air is going to contain how many molecules? 6.022 times 10 to the 23rd. And it turns out that 21% of those molecules are 21% are oxygen. Oh, a red pen. Red's usually used for oxygen. But I don't have a red pen, so I'll use orange for oxygen. So 21% of the molecules, Avogadro's numbers are oxygen. And then nitrogen is usually what color? Blue. And so 78% are, actually 78% are nitrogen. And so this is going to give us something called the mole fraction. The mole fraction is this. If it's 78%, actually let's do this. Well, I'm just going to keep it simple. We're going to call our air 79% nitrogen, 21%, or is it 22%? No, 21%. So we'll just do that. So this is assume it's 79%. It's actually 78% and 21 plus 1% other. And we'll go 79% nitrogen, 21% oxygen, just to keep our life a little simpler. So what's the mole fraction? The mole fraction we could do. We could count the number of particles and then do that, but we're not going to do that. We're just going to say that 79 moles of nitrogen for every 100 moles of air. So if I only have 1 mole of air, which I do, then it's 0.79 moles of nitrogen. So I have 0.79 moles worth of nitrogen, the blue in here. Does that make sense? And then I'm going to have 21 moles of oxygen for every 100 moles of air. And so in this container, I'm going to have 0.79 moles of nitrogen and 0.21 moles of oxygen, and this is 1 mole. of gas. So we could use the mole fraction to figure it out as how many moles. And the mole fraction, this is always true. So what happens if I increase the temperature? Does mole fraction change? If I increase the pressure? If I increase the volume?
Yes.
Of course.
Does the mole fraction change?
Fraction?
No,
No.
it doesn't. It's always true. All right, then what I'm going to do is I'm going to just pick normal pressure. What's normal pressure is 1 atmosphere, and normal temperature, which would be 25 degrees Celsius. All right, there are two ways to visualize this gas mixture. One, we can visualize this gas mixture as being a constant pressure mixture. A constant pressure mixture and temperature would be what we call Avogadro's. So what I'm going to do is I'm going to remove the nitrogen. If I remove the nitrogen and keep the container size the same, what's going to happen to the pressure? In other words, I'm going to take out all the orange ones, the red ones here, and if I remove all the red ones here, am I going to have as many collisions with the wall? No, the pressure is going to drop. So in order to maintain constant pressure, what I need to do is I need to shrink down the volume. Do you know how much I have to shrink down the volume by? Or
The same amount you
It's
did now.
gonna be,
yeah, in fact, I'm going to have to shrink the volume down to point. Well, actually, no. This is. Let's do it this way. I'm going to do it like this. I'm going to have to shrink down the volume by 79 out of 100 parts of 24.5 liters. And so, what's that volume going to be? In other words, it's going to be about 80% of the volume in order to maintain that. 19.355? Thank you. So we have to put this in a 19.355 liter box. And that way we can maintain constant pressure. And so what is the pressure going to be? Well, the pressure is going to be, okay, this is it. We're going to characterize it. I have the pressure of the nitrogen, which is going to be 1 atmosphere. And then I'm going to have the volume of the nitrogen. This is going to be 19.355 liters. And the temperature is going to stay the same. Temperature is for T. Okay, then I'm going to remove the oxygen or remove, in order to maintain constant pressure, the oxygen box has got to shrink. And do you know what the volume of the oxygen box is going to be?
5.145 liters.
Yeah, 21% of that. And that was 5.45 liters?
5.145 liters.
5.145 liters. Okay, thank you. Oops, wrong color. So, what we're going to end up with here is the pressure of the oxygen is going to be 1 atmosphere. And the volume of the oxygen is going to be 5.145 liters. 5.145 liters. And the temperature is room temperature. And so in Avogadro's, says that the total volume, which is equal to the volume of the air, is equal to the sum of the partial volumes. Sum of the partial volumes. And the sum of the partial volumes is what, well, we have volume of nitrogen, which is 19.355 liters, plus the volume of the oxygen, which is 5.145 liters. And so this should add up to 24.5 liters. And so I'm just going to say 19.4 liters plus 5.1 liters, which gives us 24.5 liters of air. Does that make sense? And so we just take our nitrogen and add it to the oxygen, and the volumes are additive here. So this is like in the KClO3, we generated some oxygen and we just added it to the air that was already present, and the volumes are additive. As long as the pressure is the same, and we can just add them up. Yeah, pressure and temperature. Which we did. We made sure the pressure was the same by equalizing pressures each time with atmospheric pressure. The second type of mixture we have is what we call a constant volume mixture. Constant volume mixture is Dalton's. So I'm going to take my 24.5 liters of air, and then what I'm going to do is I'm going to make 24.5 liters of oxygen, or not oxygen, let's do nitrogen. So I'm going to have 24.5 liters of nitrogen. Okay. Oh, I forgot to do one thing. The pressure of the air, okay, if I take, let's say, I have, how many atmospheres of nitrogen did I have? So I had 1 atmosphere of nitrogen, and how many atmospheres of oxygen did I have?
1 atmosphere.
1 atmosphere. So if I take 1 atmosphere of nitrogen plus 1 atmosphere of oxygen, how many atmospheres of air do I get?
1 atmosphere.
Yeah. In this case, I'm going to get 1 atmosphere. That's because how we add the boxes. We add the boxes together like that. And so what we don't do is we don't add these. This is Dalton's law. Dalton's law says that the total pressure is equal to the sum of the partial pressures. That's not the case. Here I have to get rid of that and then just write in equals. The pressure is constant. It doesn't change. So over here, I'm going to put all the nitrogen in a 24.5 liter box. What's going to happen to the pressure of the nitrogen? Is it still going to be at 1 atmosphere? No, it's going to go down because now we don't have any oxygen in here. And so what is the pressure of the nitrogen?
0.79.
Yeah, the pressure is we just take the mole fraction, which was 79 out of 100, and multiply that by the pressure, 1 atmosphere. What does it come out to? 0.79 atmospheres. And how many liters? Well, we have 24.5 liters. And the temperature is just RT, room temperature. Plus, where'd the oxygen go? Well, the oxygen we're going to put in a separate box, and it's going to be the exact same size box. But there's going to be very little here. And so the pressure of the oxygen, this is what we call the partial pressure, is equal to the mole fraction of the oxygen, 21 over 100, times the pressure, 1 atmosphere. So this is going to be 0.21 atmospheres of oxygen. And the volume of the oxygen is going to be 24.5 liters. And the temperature is RT. And so in Avogadro's law, the total pressure, that is the air pressure here, the pressure of the air is equal to P total. And that's equal to the sum of the partial pressures. And so the sum of the partial pressures is the pressure of the nitrogen plus the pressure of the oxygen. So the pressure of the nitrogen was 0.79 atmospheres. And the pressure of the oxygen was 0.21 atmospheres. And so that's going to give us 1 atmosphere. Whereas the volume doesn't change. So the volume of the air is equal to the volume of the nitrogen, which is equal to the volume of the oxygen. So we have to decide how we're going to treat it. We're either going to treat it, the mixture, as a constant volume, Dalton, or we're going to treat it as constant pressure, Avogadro's. But we can't treat it both. Dalton's and Avogadro's simultaneously. The weird thing about our lab was initially we treated it as Avogadro's, equalizing the pressure. And then in the lab, we switched our thinking to Dalton's when we did the partial pressure of the water vapor. And so overall, this is it. The mole fraction, which is Na over N total, is equal to the pressure fraction, well, actually, let's do the volume fraction, is equal to the volume fraction, VA over V total, which is equal to the pressure fraction, PA over P total. However, these cannot be simultaneously true. And so this is always true. This one is only if constant pressure. So if we have constant pressure, then this one cannot be true. And so if this is true, this is false. Likewise, if the pressure fraction is true, then the volume fraction is false. And so only if constant volume. Okay, with that, gas mixtures. So when we do problems, we have to just make sure we're consistent. And we need pressure, volume, and temperature. And we want to make sure that we use the correct volumes and the correct temperatures and the correct pressures for the calculation.
So this would be, was it a volume fraction and a pressure fraction, right? Is equal to the mole fraction.
Yeah.
The N over N is that mole fraction.
Let's say I'm looking at the mole fraction of nitrogen. The mole fraction of nitrogen is 79%, or 79 and 100. I can convert a fraction into percentage by multiplying by 100%.
Is there a temperature fraction for a TA is equal to T total?
No. So for example, I wouldn't do both. So remember the mole fraction of nitrogen's 78%. Would I say, okay, that means both the volume is 78%, so it's 78% size like this, and the pressure is 78%? No, one or the other. So if I said, okay, the mole fraction is 78% nitrogen, then I could say the volume is 78%, but the pressure won't be. The pressure would be the full pressure. Or I could say the mole fraction of nitrogen is 78%, and the pressure must be 78% of the total. But the volume has to be 100% of the total. So we just have to be careful because people get those mixed up all the time. We're going to go on to 6.7 and talk about 6.7 and 6.8, kinetic molecular theory. Kinetic molecular theory of an ideal gas. Kinetic molecular theory states that if you have a gas sample, it consists mostly of occupied space or empty space? Empty space. And so this is mostly empty space, and then we have tiny particles of gas. Now, does the ideal gas law ask you what kind of gas that is? Does it ask you if it's steam or helium? No. It treats steam and helium the exact same, but would you treat steam and helium exactly the same?
No.
Not really, I think. The steam is not so ideal. Helium is very ideal. Helium is a great gas. You know, helium stays a gas all the way to what temperature?
0 Kelvin.
No, very close.
4 Kelvin.
4 Kelvin. Helium almost makes it all the way to 0 Kelvin. And helium is the most ideal gas there is because at 4 Kelvin it liquefies and then it's no longer a gas. There's no such thing as a true ideal gas. There's no gas that will survive all the way to 0 Kelvin.
Find a gas that's right now.
But, you know, at high temperatures, steam behaves pretty ideally. You know, as long as you keep the temperature high, then it behaves. But what we see, when we represent the molecular theory, there's no rotations because all the gas particles are the same, and there's no vibrations because there's no bonds. In an ideal gas, you just have little points, and these are the particles. And the particles are just little spheres or little dots. In fact, the particles' volume is negligible, close to, compared to the size of the container, close to 0. And these are moving in random motion. But there's collisions. When they collide with the wall, you know, we have two types of collisions of extreme. At one extreme, we have an inelastic collision, and the other extreme, we have an elastic collision. Do you know the difference between an elastic collision and an inelastic collision? Like, okay, let's say you take a soft clay ball and you threw it at the wall, like a wet, soft clay ball. What's it going to do when it hits the wall? It's probably just going to stick. Is that an elastic collision or is that an inelastic? Inelastic. Whereas, let's say you have like an 8 ball from a pool table and you threw it at the wall, it probably just bounce off, right? A rubber ball.
I was thinking it was going to go through the wall.
Well, it probably goes through the wall. You probably don't want to throw it
Yeah,
at the wall.
rubber ball though.
Yeah, let's take a rubber ball. A rubber ball would be an example of a
Elastic.
except, you know, the rubber deforms, so it's going to lose a little bit of energy. When we think about this, we think about the optimum elastic collision in which it just bounces off without losing any energy at all. And so we have these elastic collisions with the wall, and we have the elastic collisions with each other, you know. So if you have two water molecules, do they just bounce off each other elastically, or are they kind of sticky? They're kind of sticky. So water's not so ideal because it's kind of sticky, likes to stick to itself. It also likes to stick to certain things like glass. And they're moving. So do you know how fast heliums are moving?
So fast that you have to reduce the time down to like 1 picosecond.
Yeah, they're moving. They're moving. Well, it's not that fast. How fast are heliums moving? About. Let me take a look. Got it. We could calculate it. Do you know how we could calculate it? We could calculate using the equations of kinetic molecular theory. And so let's see what the equations of kinetic molecular theory are. Although I did have a number. I think it was about 3,000 miles an hour. Well, 3,000 miles. And then, do you know how fast CO2 moves?
No.
About 1,000 miles an hour. Or was it? Or 500? Maybe it was 500 miles an hour. But what we're going to do is, we don't have to guess. We can actually calculate it using the equation from
moving at 646 miles per hour.
kinetic molecular theory. And so these are the basics. A gas is composed of a very large number of extremely small particles. The molecules are in some cases atoms in constant random straight line motion. Molecules of a gas are separated by great distances. You know, they're great distances because gas particles are so small. The great distances might be centimeters. You know, that would be a great distance if you have the size of an atom. The gas is mostly empty space. The molecules are treated as so-called point masses, as they have mass but no volume. You know, an ideal gas is to shrink to zero volume. The only way it can shrink to zero volume is to have zero volume, but you know, it's not going to necessarily happen. Molecules collide only fleetingly with one another and with the walls of their container, and most of the time molecules are not colliding. There's certain things that we do. There's other things we can calculate. We can calculate, okay, what did I say? The speed. We can calculate how many collisions occur per second. How many collisions occur per second is collision frequency. So what do you think the collision frequency is, like at normal ambient conditions? A lot. A lot. It's a huge number. Like millions per second or more or less. We'll take a look at that. And we can also calculate how far it travels on average before it collides. You know what that's called? The mean free path. And so it depends on the vacuum level. You know, if you're close to a perfect vacuum, then that particle can travel miles and miles before hitting anything. If you're close to room temperature and atmospheric pressure, then it doesn't travel as far. There assumed to be no forces between molecules, so the molecules can't be sticky. If the molecules are sticky, then they aren't very ideal. That is, each molecule acts independently of all the others and is unaffected by their presence, except in an elastic collision. Okay, so we have this speed. Do you remember the distribution of kinetic energy? Well, we have three types of kinetic energy. Ideal gases only have one type of kinetic energy. Do you know what it is? Translational motion. Translational motion is, we usually represent that with how fast is that moving? You know, how fast is that translating? And we're going to have a distribution. What's that distribution called?
Maxwell-Boltzmann.
Maxwell-Boltzmann distribution. Do you want to know what the Maxwell-Boltzmann equation looks like? This. No, you don't need it.
Oh, cool. I will not copy that.
So if you're ever curious about what the Maxwell-Boltzmann equation looks like, this is the Maxwell-Boltzmann equation, which defines the Maxwell-Boltzmann distribution. But we're not going to do any calculations with the Maxwell-Boltzmann equation or the distribution. You just have to know the shape of it. So the equation above is called the Maxwell-Boltzmann distribution of speeds in honor of James Clerk Maxwell, who first derived it in 1860. And Ludwig Boltzmann, who later provided significant insights into the physical origins of this equation. We will not attempt to derive the distribution, because to do so requires complex mathematics. Instead, we will accept it as valid and use it to help us understand how the distribution of speeds depends on molar mass and temperature T. So we're going to use this equation, but we're going to use it kind of in a simplified version of this equation. Do you recognize this curve? What is this curve called? This is called the Maxwell-Boltzmann
It's just called Max.
distribution.
His name's Max.
This shows the population. In this particular case, it's the percentage. So, you know, this all has to add up to 100%, basically. So this is the total population. The greatest percentage will have the speed. This is the speed, how fast they're moving. And the speed is given what symbol? In physics, usually you use the symbol V. V for velocity. Velocity and speed are the same thing. Here, what symbol are we using? Not V. You know what we're using? U. We're using U for the speed. So how fast is hydrogen moving? Well, this is hydrogen gas at 0 degrees C. At 0 degrees C, does hydrogen behave pretty like a gas? Or does it liquefy at 0 degrees C? It doesn't. No. Hydrogen liquefies at much, much lower temperatures. And so this is behaving like a gas. How fast is hydrogen moving? Well, I asked you how fast is it moving, but in reality, we have a spectrum of speeds. This is at 0 degrees C, so some of the hydrogens are moving slow, some of them are moving fast. So when I ask you how fast they're moving, it's a little bit tricky because we have a distribution of speeds that they're moving.
Didn't you say they all have the same energy, or is that only
No, they do. They have what we say is this distribution has the same, what we call average kinetic energy. This is the problem with thermodynamics. And people who don't keep track of all these little things, like little labels, have a hard time with thermodynamics. And so you have to keep track of all these little things, like this. UM, UAV, URMS. Right. If you just say speed, then people don't know what you're talking about. You have to specify. Like, for example, UM. Do you know what UM stands for? Okay, here, let me scroll.
Most average.
The most.
Most probable.
The most probable, the average,
Probably
and the
maximum.
root mean square speed.
Right, you got it. So the most probable speed is, well, what's the greatest population of molecules? When we look at the greatest population of hydrogen, it's at the peak here. And so that's the most probable speed because most of the hydrogens are moving at that speed. And so the most probable speed is at the peak. But we don't do much with the most probable speed.
To the average.
Well, the average speed, this is not in the center. Why? Because this distribution is skewed, right? You see that? And so the distribution, the average is going to be slightly to the right. We really don't do anything with the average either. And so the average speed, you know what we do? Use quite a lot?
Root mean square.
The root mean square speed. Now, what is the root mean square speed? So if somebody asks you how fast hydrogen is moving, you'd say about 1,800 meters per second because that's the RMS speed, root mean squared, RMS speed. Right? 1,800 meters per second, which translates to like 1,000 miles an hour, I think. We can calculate it using dimensional analysis, but
I would say
we'll
that's 18,000 meters per second. It's a lot more than 1,000 miles per hour.
This is a lot more. Maybe it's 2,000, 3,000 miles an hour. 18. Let's just do. Let's do meters per second to mph. And let's do, what was it? 1,800. Unfortunately, you can't use this on the tab. You're gonna have to calculate it. But I don't want to calculate it.
I would say if we assume that it's 2 miles per hour for every meter per second, that would be 36.
Right. 4,000 miles per hour. That's at 0 degrees C. 4,000 miles
Wait, that's
per
how
hour.
fast hydrogen's going?
Yeah.
Is that what we figured out?
Yeah, that's how fast it goes when it's freezing outside.
I love that.
Well, that's how fast it's going at RMS. But what is RMS? RMS is you take the mean, you square it, and square root it. And you don't have to worry about, what the heck is that? If you take the mean and square it and square root it, aren't you going to get the mean again?
No.
Why?
I guess not.
It's because when you root something, unless it's defined as a positive integer, it would see the positive or negative, which means that it's either going one direction.
Yeah, it could be plus or minus. So wouldn't it be just a plus or minus the mean?
Yeah.
So if you take the mean, square it, and then take the square root, didn't you just undo the square? Well, don't worry about the math on this. We don't have to worry about the math. But let's worry about what the RMS represents. What the RMS represents is we have a distribution of hydrogen. Some are moving slow, some are moving fast. Right? Some are moving at 4,000. 4,000. What would be 4,000 meters per second be?
16,000 miles per hour. No.
About 9,000.
Yeah.
9,000 miles an hour. So some of these are moving 10,000. Well, 4,500 is 10,000 miles an hour. Gee, that's fast. And so what we have here is this, but it's a very small population. Most of them are moving at about 1,500 meters per second here, and some of them are moving slow. So what the RMS is if you take that whole collection, 100% of the population, and assign them the exact same speed, what would the speed be? And that's the RMS. The RMS is the effective speed. So I'm going to take this entire population and just collapse it into one speed. So the fast ones will give their speed to the slow ones, and everybody will come out the same. And the same would be 1,800 meters per second. And so when we talk about the energy is related to temperature, right? And so there's some things. So we need some additional equations here that we're going to use. Sure. Do that. Yeah. So we're not going to use equation 618. Here are representations of experiment 618. Why is this? Look at hydrogen at room temperature. Or this is not room temperature. This is 273. This is 0 degrees C. Look at hydrogen at 0. Look, why is oxygen so much slower? Do you see it? The RMS, where's the RMS speed going to be around?
For hydrogen?
Yeah, for hydrogen, it's over here, right?
I was gonna say a little bit more back.
A little bit here. Where's the RMS speed for oxygen? How come oxygens are moving so much slower? You know, RMS is the effective speed of the population. And oxygen is at 0 degrees C, it's moving a lot slower. It weighs a lot more. They're a lot heavier. They're a lot heavier, but you know what? They're going to have the same kinetic energy. And so the effective kinetic energy of the hydrogen will have the exact same effective kinetic energy as the oxygen, because they're both at the same temperature. Temperature is a measure of kinetic energy. And so we're going to be using a couple of equations here. Okay, the first equation we're going to encounter is the RMS speed. So we're going to be able to calculate the RMS speed here, which would be like the effective speed for the collection. So U RMS is equal to the square root of 3 RT over the molar mass. So when we look at the units for this, the molar mass is going to be in kilograms per mole. R is going to be in joules per mole Kelvin. And a joule is the same thing as a kilogram meter squared per second squared per mole Kelvin. T is going to be in Kelvin here. And so what we end up with is kilograms cancel, Kelvin cancels, moles cancel, and we're left with meters squared per second squared, and we take the square root of that, and we get units of meters per second for URMS. We're going to use this R value, 8.3145, if you want it to 5 sig figs. Joules per mole Kelvin. So we're not going to worry about the average or the mean. We're just going to worry about the RMS. The reason we're going to worry about the RMS is because in physics, do you know how to calculate the kinetic energy, what the kinetic energy is equal to? If we only have translational motion, then the kinetic energy, which our book calls E sub k, and we use this bar. Do you know what that bar means? Average. So this is the average kinetic energy. The average kinetic energy is equal to 1/2 mu RMS squared. So in other words, 1/2 mv squared is the equation that people have to memorize in physics. This is only for translational energy, and there's only translational energy in an ideal gas. If we're looking at a real gas can have rotational and vibrational. And so we have to add extra terms to this to get the kinetic energy of a real gas versus an ideal gas. There's one more thing, one more equation, and well, that's this equation here. And why do they go with capital? They used to use lowercase. There's one more thing that this is equal to. And so E bar K, the average kinetic energy, is also equal to, this is from kinetic molecular theory, 3/2 RT over Avogadro's number, N sub A. And so the average kinetic energy is directly proportional to the temperature. So if we double the temperature, this is absolute temperature, by the way, not Celsius or Fahrenheit temperature. If we double the temperature, we've just doubled the kinetic energy. And that's going to shift. If we double the temperature, that's going to double the kinetic energy, which is going to increase the speed by how much? Will it double the speed, RMS? No. No. And so it's the square root of 2 times RMS. All right, so those are the main equations of kinetic molecular theory. They go through a derivation. We use this kinetic molecular theory to derive all the simple gas laws, and we could use kinetic molecular theory to derive the ideal gas law. This chapter goes through some of the math in the derivation of this. We're not going to derive this. We're going to skip all this stuff. But it talks about collisions, etc.
Wait, Professor, what does the lowercase n stand for?
What does the lowercase n stand for?
N. The
M?
lowercase n.
Mass.
Mass.
Yeah,
Okay.
that's going to be the mass of the individual particle.
Okay. Make sure it's mass, not something else, because it's also in italics.
Yeah.
And with the capital N and then the capital N in italics.
Yeah. Yeah. In this case, it's just mass.
Yeah, because they have meters per second.
This funny thing is the mean squared speed here.
It's Y, Z, all the X.
Yeah. All right. So the applications of this one, we want to calculate the RMS speed. 2, we want to see that the kinetic energy is related to the U RMS speed, and the kinetic energy is directly proportional to temperature. We don't really do too many calculations with this kind of stuff here. With this. And then the application of this is diffusion rates. And so one of the applications is comparing effusion and diffusion. If something's moving faster, then it can diffuse through the room faster. So for example, a light molecule, you know what? If I have a light molecule, will it go straight to the back of the room? Let's say it's traveling this direction. No, what happens is it undergoes many, many collisions. So by the time a light molecule makes it back to the end of the room there, it's already traveled probably many, many miles. And so that's called diffusion. You know, it takes time for gas to diffuse through a room or through air because of all the collision. Effusion is escaping out of a pinhole. You know, if I have a gas trapped in a container like this, like helium, you know, helium will escape out of a pinhole much faster than air escapes. Air is a lot heavier, about 28 versus helium about 4. And so helium escapes a lot faster out of there. And so when we compare the rates, we can come up with Graham's law. Let's see, do I have Graham's law here? Yeah. here's some diagrams of, this is diffusion here. Mixing. This is effusion here. And we use Graham's law here to do this. And so let's compare the two rates. The rate of A over the rate of B is equal to this. The rate of B, A is going to depend on how fast A is moving. How fast A is moving is going to equal 3RT over the molar mass of A. And the rate of B is going to depend on how fast B is moving. So this is going to be 3RT over the molar mass of B. The RTs are the same and 3 is the same. And so we end up with this is going to be inversely proportional to their molar masses, the square root of their molar masses. And so that's what we see at the end over there. The rate is also inversely proportional to the time. So we could add one more thing. The faster it's moving, the shorter the time it takes. And so this would be the time it takes for B over the time it takes for A. And so we can calculate how long it's going to take to move through there. And so that's one additional thing we could add to that.
Is that just for diffusion?
And diffusion, both.
Oh, okay. I have to say, it's just to say diffused.
Yeah. And so there's some examples, how many times faster will it be or slower will it be. Here's a derivation of Graham's law. We don't need the derivation of Graham's law. Applications of diffusion. Up to this point, we have focused more on effusion than on diffusion. However, diffusion of gases into one another has many practical applications. Natural gas and liquefied petroleum gas, LPG, are odorless. For commercial use, a small quantity of gaseous organic sulfur compound, methyl mercaptan, is added to them. Do you know natural gas stinks? But natural gas has no odor. They have to add, and what has a nasty odor? Sulfur compounds, right?
It smells like
And so in natural gas, we add, you know what we call this one?
mercaptan.
Yeah, this is called methyl mercaptan or methanethiol. Like methanol, but it's not always except it has sulfur.
Oh, so we use that.
Yeah, mercaptans are alcohols with sulfur. The mercaptan has an odor that can be detected in parts per billion or less. Yeah. When a leak occurs, which can lead to asphyxiation or an explosion, we rely on the diffusion of this odorous compound for a warning. So it better diffuse fast. I mean, if they picked a heavy molecule, there's going to be too much delay. That's one application. Another application is during World War II, the Manhattan Project, the secret U.S. government-run program for developing the atomic bomb, used a method called gaseous diffusion to separate U-235 from U-238. The method is based on the fact that uranium hexafluoride is one of the few compounds of uranium that can be obtained as a gas at moderate temperatures. So what they did was they made uranium hexafluoride, and you have two isotopes. So the heavier one's going to move slower than the faster one. And so if the distance is long enough, then they can separate it. It's like a marathon. They might start off the same, but after a long distance, they aren't going to be the same.
I believe uranium hexafluoride is also used in the creation of nuclear fuel.
Yes. Yeah.
I'm not sure what
Purification.
I'm not sure what it makes, but I remember hearing something about it.
Yeah. They use it for different things. Okay, the last section is non-ideal real gases. Now, what makes an ideal gas are two things. One, the volume has to be so small, it's zero for practical purposes. And two, the molecules can't be sticky. Okay. So hydrogen is not very sticky. You see this black dashed line?
Mhm.
That's the ideal gas law. This is what the ideal gas law predicts. Do you see these curves, the green, the blue, and the red? That's what the experiment shows. So I said laws, remember when I was talking about laws versus rules?
Yeah.
Laws are not to be violated. Rules can be violated, right? But the ideal gas law is a law that's violated quite a lot. Unless you stay right in this little area here. Do you see right in this little area, the ideal gas law works pretty well. But as soon as you go outside this little area, we see large deviations from the ideal gas law. But that little area is fine for us, because how often do you work at 200 atmospheres of pressure?
Never.
Hopefully never.
Well, maybe some people do.
Never.
200, 400, 600 atmospheres. 1,000 atmospheres? If you're trying to make diamonds, maybe 1,000 atmospheres we'll be working at. And so we're okay because most of the time we're working at 1 atmosphere, which is right there, and most gases behave ideally because they're on that black dotted line. But as soon as you get to about 10 atmospheres, we're already in for massive deviations.
Well, as we start at 0 atmospheres.
Yeah, 0 atmosphere is fine. From 0 on up, at 0 atmospheres, gases behave extremely ideal. And so the lower the pressure, the better. What happens is, as you go to higher pressure, you're forcing the molecules closer. And when molecules get closer, then they can stick to one another. And so which of these 3 molecules are the stickiest? CO2 is the stickiest, and that's because of what we call dispersion or London forces. CO2 is a normal polar. And so they start to stick to one another. And so we get that deviation. And then as we go to higher and higher pressures in the volume, hydrogens aren't very sticky, but as we go to higher and higher pressures, then the molecules get more and more cramped. And as they get more and more cramped, then they need more room. They don't have enough space. And so the volume impacts it. And so we see impact of 2 things. We see impact of stickiness and volume. And at extreme pressures, things are getting cramped because there's not as much empty space. When there's plenty of empty space, then it's fine. Nobody cares. And so one attempt at correcting for this is by using the van der Waals equation. The van der Waals equation says that the pressure, normal pressure, this is PV equals nRT, right? But take a look at what happens to the pressure. The pressure of a real gas is going to be less than the pressure of an ideal gas. Because the pressure of an ideal gas equals this whole term, depending on how big this term grows. The bigger this term grows, the smaller this term becomes. And so this is going to depend on N over V. You know what N over V is? The number of moles per volume. So it depends on how close they are. The greater the moles per volume, the greater the impact. And it's squared, but we won't worry about that. Times A. A is the stickiness factor. How sticky are these? And so let's take a look at that A factor here and try to predict or look at these here. So A is the stickiness. So which one is the least sticky? Ideal gas, because there's no stick at all. They don't stick to one another. Helium's pretty close, right? Helium's not sticky, or minimally. Which of these is the stickiest?
From what I can see, it's C3H8.
Yeah, well, it's propane. Propane's the stickiest. And when you buy propane, it's easy to liquefy. When you get a propane cylinder, you can swash around the liquid propane in the tank. You can hear it. And so that's the stickiness factor. And so the stickiness factor, intermolecular forces. So A is related to the intermolecular forces. Now B is related to volume. How much space is occupied by the molecule? So this is liters of space per mole. And so if I had a mole of these molecules, how many liters does that take? So for example, if I had a mole of ideal gas, it takes 0 liters. But if I have a mole of helium, then it occupies 23.8 milliliters of just the of the atoms alone. So if I were to liquefy the helium, I'd get 23.8 liters in a mole. Does that make sense?
Yes.
Okay, which one of these molecules is the biggest? Looks like propane, right? Propane is going to have 90.5 liters per mole of just molecule space, molecule volume. Okay, so the two factors are going to impact things here in this equation. The B is how much space the molecules or particles occupy, and that's going to cut down. If I have 1 liter of gas, it's not 1 liter of empty space. It's 1 liter minus how many liters the particles themselves take. And so that tweaks the equation. So this is a tweaked version of the ideal gas law to help compensate for non-ideal behavior. Okay, I guess we're out of time. So this is the last section of this. So we use that equation. This equation, we have to know what the gas is. Ideal gas law, we don't have to know what the gas is.
We assume that every gas is ideal.
Yes, right. We just assume every gas is ideal.
So this is the non-ideal ideal gas law.
Yeah.